So what are some of the strengths and weaknesses of k-means? I've mentioned it before, and it's not an exaggeration to say that that's like one of its main strengths. It is excessively easy to implement. And you don't typically have to compute the pairwise distances, which is good. So a consequence of that is that it's very common, it's very elegant, it's very simple, and in many ways, many contexts, k-means is the natural way to look at grouping observations. So it's not a coincidence that it's so commonly used. Worst case scenario, as a first pass, k-means provides you with a basic understanding of the data structure, of what you have in your data set. So you will never fail by having k-means be part of your picture. It can't be the only thing in many instances. You got to go past k-means. The limitations: every point can only be assigned to one cluster. Again, there's many instances where this would be a natural thing to do, but there might be instances where you would like points to potentially be assigned to more than one cluster, have a probability of belonging to a cluster, because there could be overlap of clusters in general. So that can lead to overfitting. That's problematic. Probability of belonging to a cluster is better. It's that in expectation maximization, for instance, talks about, at least for every point, it gives us a probability that it would belong to a given cluster. That's probably a more reasonable approach. You are assuming that the underlying clusters are blob-shaped. They have to look like round things, basically data that is generated by some normal distribution. If that assumption is not met in practice, k-means will not produce useful clusters. The clusters are assumed to be separate, to be discrete, but there might be many instances where the clusters would be overlapping, and k-means does not allow you to sort of identify those. Rather than find two overlapping clusters, it's going to find one big cluster with a weird structure to it. What are some of the distance measures you might use if you're working with categorical variables, which you may need to dichotomize first? You have the Hamming distance, which we've talked about. There's the Jacquard distance, we've talked about as well. There's other categorical distances, the Russell-Rao index. You can look at matching coefficients, Dice's coefficient, and so forth. Numerical variables, Euclidean, Manhattan, correlation, cosine, Pearson. There's tons of these things that exist. If you use different metrics, you will potentially get different results. That's not necessarily a bad thing, but you need to be aware that the choice of metric dictates in many instances what the results would be. If you're going to be working with mixed data, which is to say you have numerical data and categorical data, if your numerical data, you decide to compute the distance, at least for the part of it, using the Euclidean distance, for the categorical data, you should use the Hamming distance. And then you combine them together. What's the distance between two observations? You compute the Euclidean distance between the numerical parts. You can compute the Hamming distance between the categorical parts, and then you add these results together, and that's the distance between the two observations. If instead you're using the Manhattan distance, for instance, for numerical parts, you should use the Jacquard distance for the categorical part. Okay, so there's typically a better suited categorical distance for each choice of numerical distance, and vice versa as well. What are some of the challenges? Look, it is easy to automate them and it's easy to write the code for it, but you don't have an easy way to audit the process for a computer. Human beings can look at these things and say, no, this is wrong. This is not the kind of stuff that I had in mind. The computer does not. So if you automate it, if you leave the clustering algorithms arm's length, and you never go and check into what's happening through the automation process, you are going to end up with ridiculous results. Okay? So you can't just leave it in the hands of the computer. There's got to be fairly constant human involvement. The lack of a clear-cut definition of what a cluster is, that's problematic. If we can't agree on what a cluster is, how do we compare what the results are? The lack of repeatability is a problem as well. If your algorithm is if your algorithm is non-deterministic, you apply the same result twice, you get completely different results. What do you do? Oh, there's an easy solution for that one. You never run it just once. You run it multiple times, and you look at the convergence. How do you pick the optimal number of clusters? That is difficult to determine, especially if your data is multi-dimensional and you have mixed variables in there. How many clusters do you find or do you see in this data set? Well, I see 3, I guess. These 3? But why are these 3 clusters and this one not a cluster? If I was to say remove some observations, if these 3 big clusters weren't there, and I remove a bunch of observations, perhaps these observations would look like they're similar. So the number of clusters is also relative to the distribution of the points to start with. And if you look at subsets of the data, things that wouldn't have struck you as likely to belong to a cluster might strike you now as, yes, that's definitely part of a cluster. It is fairly arbitrary. How many clusters do you see in this data set? Two, 1. What is it supposed to be? There's one cluster which is a blob. So there's a very good k-means cluster right here. But then you get a bunch of points which seem to have something in common. They have the boundary in common, but that's not a blob. So k-means wouldn't be able to identify this as a cluster the same way that the rest of the data set would be identified as a cluster. Is this problematic? It could be. So it's not just that you can have mixed types of variables, but you can have mixed types of clusters in a data set as well. Now you'll say that never happens. This is completely artificial. It's like, no, it totally happens. How many clusters do you see in this data set? You see 4. It depends on your point of view. I mean, you have glasses as well at Quebec, so you could do the same exercise I've just done here. But if I walk back and I squint, I actually only see 2 clusters. Right? I see this cluster of points right here. There's 1, and then I see this bottom left as 1 cluster of points. The overlap here sort of like disappears in my field of the straight, I guess I would say, disappears in my field of vision, and they're collected together. There might be 4 as well. I mean, if they're all meant to be of the same type, there's this one, and there's this one, and there's one that's overlapping here. So what is it? Is there a true answer here? If you're looking at this data set from the vantage point of Alpha Centauri, 4.3 light years away from here, it looks like there's only 1 cluster. 1 second, I'm sorry, the phone is ringing. I apologize for that. So, how many clusters are there? Can't answer this question. How many clusters are there based on what it is that we want to do with it? That's a question you might be able to answer. But you need to have an end goal in mind to be able to quantify the answer. One of the ways in which you can try to determine the number of clusters is to look at, for instance, k-means here, the average distance to the centroid in each cluster. So if you think there's 3 clusters here, perhaps this is 1 cluster, bottom one is a cluster, and this one is a cluster. They each have a centroid. You compute the average distance to the centroids, and then you see, you plot that. And if you get to a kink, if you get to a point where after that point the average distance doesn't really seem to decrease that much anymore, that could be an indication that the right number of clusters is 3. But again, be careful, because this might be the result you get with one clustering algorithm with 3 clusters. Perhaps instead you're supposed to run this 15 times and basically have not just 1 point here, but 15 points for each number of clusters, and then the curve might not have a kink in the same place. There might not even be a curve anymore. So even though we can sometimes come up with a potential solution to help us decide what the number of clusters should be, it is quite likely to be that we need to do more than one run to be able to make sense out of the problem as a whole. How do you describe the clusters? And for you specifically, that's going to be an important problem to solve. Like, if you come up with clusters, like, these are small and medium enterprises. Well, I mean, you might get points in there that don't fit the profile of what people understand to be SMEs. So you might need to come up with a different description. But look, there might be 20,000 points in your cluster. There's going to be things that are, how do you come up with a short description that explains what kind of points you get in there, but with the understanding that you're going to be missing a lot of the points. And you might actually accidentally be describing points that show up in other clusters as well. This is very difficult, especially when we spend a fair amount of our time talking to non-quantitative audiences. How do you validate the result? There isn't true clustering information against which to contrast the clustering scheme. So how do you decide if it's appropriate or not? We'll talk about some clustering validation possibilities. Then there's this other problem, which at first sounded ridiculous when I heard about it, but ghost clusters. Most methods, except for dbScan, amongst the methods we've talked about, if you tell it to find clusters, it is going to find clusters. Even if there's no clusters in the data, it will say, you wanted me to find 5 clusters, you ran 5 means, here are the 5 clusters. How many clusters do you have in this data set? Well, you'd probably answer none. All the points are like there, but if you run 5 means on this, you will get 5 clusters. I mean, it's true that all these points in red are close to one another, but that's a meaningless cluster. That doesn't mean anything. And finally, the idea of a posteriori rationalization. If you found clusters, you're trying to explain why they're clusters. That is not something you can do without like serious subject matter expertise here. And even experts, if you believe the anecdote I told you previously, can completely miss the boat. So one thing I want to tell you, all of the examples I've shown you here were examples in 2D or 3D spaces. I mean, it's easy to do if you only have 2 variables. But if you work in high dimensional spaces and your points are like fairly uniformly distributed over 10 dimensions, 20 dimensions, all the pairs of points are equidistant. There is no such thing as points that are close to one another. So what does it mean to do clustering then? If points that are similar are points that are close to one another, you launch k-means or any other algorithm on high dimensional data sets and they'll get you points that have nothing in common with one another. They're all far from one another. So then you might have to do some feature selection, some dimension reduction, some manifold learning to bring your original big data set to a smaller dimensional data set on which you can run your clustering algorithms. But if you're running the algorithms on a reduced data set, especially if you're using dimension reduction instead of feature selection, the new variables that are down there don't really have any clear-cut interpretation. And so clustering is being done on these transformations of variables, and you lose your ability to really make sense of the types of clusters, being able to explain them, to come up with a labeling scheme afterwards. Pretty much no matter what you do with clustering, you're going to be faced with a wall, right? It's hard. Unsupervised learning is substantially more difficult than supervised learning. We'll use the iris data set as an example here. We're going to be running a bunch of k-means on a data set of 150 flower specimens, irises, that have been collected on the Gaspé Peninsula in the 1930s. And for each specimen, people measured the petal width, the petal length, the sepal width, and the sepal length. I'm not sure if this is pronounced. I don't know how this word is pronounced. It could be sepal, sepal, I have no idea. And we also will collect the species, although we will not be using the species as part of our variable set to determine the to plot the variables. So here is the two principal component projection of the irises. As it happens, there's a fair number of irises that are in the same species here, and they are characterized by having a small value between -3 and -1 for the first principal component. And there's two other species, and they're characterized by being, roughly speaking, one species tends to have a first principal component between -0.5 and about 1.5. The other one seems to be above 1.5. That's the characterization of the observations. Now there's some overlap, as you see here. It's not a perfect classification. So, okay, so that's the true classification. The three species of irises. This is how they're identified. Now we're going to run a bunch of k-means on them. So I ran a two-means clustering algorithm on the data set, and I asked the algorithm to find two clusters. This is the two clusters that it found. That sort of makes sense. I mean, this is sort of a blob in red, and the black one is also sort of a blob. So for two clusters, gave me more or less what I wanted. And I know I told you, if you run it at different times, you might get different results. For this one, you don't. The way this is set up is because there's a clear-cut separation between these points, you always get these two clusters showing up as clusters. So that's good. Now I asked it to do 3 clusters, and one of the runs it found these three. Oops, sorry, I went too far. One of the runs it found these 3 clusters. I mean, that sort of matches what you saw in the true classification. Not quite. K-means doesn't do this overlapping business, right? And then just for kicks, I also asked it to go to 4 clusters. Five clusters, 7 clusters, 15 clusters. It's finding a bunch of points. I mean, it's not a completely ridiculous clustering scheme. If I was asking it to find 15 clusters, yeah, that sort of looks like what you might expect to find. Well, I mean, why is this triangle here yellow and this point, triangle red and this square yellow? Perhaps, you know, they could be together, who knows? But all in all, that's not the most ridiculous clustering scheme. Like this point here is sort of identified as not really belonging to any of the other clusters. That, okay, we can live with that. And he's like, yeah, okay, that's sort of an acceptable 15 cluster segmentation of the data. But nobody would ever think there's truly 15 clusters in this data set. There isn't 15 clusters in this data set. And the same goes for 7 clusters. It's like, yeah, if I was looking for 7 clusters, that might not be a bad description of segmentation of the data set, but there isn't 7 clusters in this data set. Human beings can right away see there isn't 7 clusters. The computer just says, you asked me to find 7, I found you 7. How do we know which one is the best scheme amongst all of the schemes that we've computed, all of the results that we found? Which one is the best? Does it make sense to say that a scheme is better than another scheme? Does it make sense to ask if a clustering scheme is valid or not? Is this valid? Is this good? These are difficult questions to answer. How many clusters are there? Like, the main challenge is, what is it that we're comparing the results to? And all unsupervised tasks have this problem. It is not, in my mind, ideal to ask, is this the right clustering scheme or the wrong one, or is this good or bad? That these questions are meaningless to me. I think the meaningful question is to ask, is this optimal or is this suboptimal? And if it is suboptimal, can I still live with the results? Can I do something with it? Can I achieve my ultimate end game, end goal with the potentially suboptimal clustering? So what does it mean for a clustering scheme to be optimal? There should be maximal separation between the clusters. However you measure separation, however you measure distance, that should be maximized. And there should be maximal similarity within the groups. You want your observations to be very similar. It should agree with the human eye test whenever you can display the information in a low dimensional space that humans can consume. And it should, and this is very important, you should be able to use your clustering scheme to achieve the goals that you have in mind. You can have maximal separation between clusters, maximal similarity within groups, could agree with the human eye test, but if you can't use it to achieve your goals, it's pointless. It's suboptimal. It doesn't help you at all. 3 types of validations we'll consider, and again, we will revisit this in much more detail because to my mind, this is the most important aspect of clustering. You can use external validation, comparing your results to, well, some other external additional information that comes in after the fact, information that you did not use to cluster the observations. You can use internal validation, so you're just going to be evaluating by comparing, by using the actual clustering result itself. And then you use relative, you compare across different clustering attempts. For my money, the best approach is relative. But it could be costly to run different attempts, so internal might work best. External is the one that's the most tempting to use, but it's a happy accident if external validation works for you, but in general you can't really conclude anything from external validation. You can use something like the Davies-Bouldin index, say. This is an internal, well, I guess you could say internal, also relative. You compute a metric for each clustering result. You compute a value that decides or tells you whether things are very maximally separated across different clusters, and if the similarity is maximized within a cluster. So it's a maximum quantity. That's not, how it's defined is perhaps not super important, but the point is that you can come up with numbers there. You can use other methods, sum of squared and errors, Dunn's index, silhouette metric. We'll talk about Dunn's index and silhouette metric a little bit as well. But here, I'm plotting what the Davies-Bouldin index would look like for a number of clustering schemes. and for number of runs. And what we're getting there is that this index is maximized when I think I have 5 clusters. We're seeing that there's not a lot of variation amongst the Davies-Bouldin indices, because if you're running only 5 clusters on this data set, k-means always finds the same, up to 5 I mean, always finds the same clusters. When you get a bit further out, when you're running more clusters, then the stochasticity comes into play and you get different results. But it's maximized when you have 5 clusters. So this would seem to indicate that according to k-means and the data set that we have, there should truly be 5 clusters in the data. If you use the sum of squared errors, this is the same thing I had shown before. Roughly speaking, you compute the average distance from each centroid to the points in the cluster over the different number of clusters. You get, well, you look for points where there's a kink in that chart. And there's a kink after 3 clusters or 3 clusters, and there's another kink at 5 clusters. These two results combined together seems to suggest to us that there truly should be 5 clusters in general in the dataset. So here I did one replicate of the 5 clusters on the original 4-dimensional dataset, and I get that these would be the 5 clusters. This is what it understands to be the 5 natural groups of observations in the dataset as a whole. So one of the groups here has been divided into 2, and the other group, the other chunk, has been divided into 3 different clusters. It is complicated to validate clusters. I know I've said it 5 times already. Let me say it again. It's not an easy thing to do at all.